Hello class, in this video we'll be doing another example on how to use the fundamental theorem of calculus to evaluate a definite integral. Let's begin. So we want to evaluate the definite integral from 0 to 2 of this function right here. And before I can do that, I have to answer the question, is the function continuous on the closed interval 0 to 2? And my answer to that is yes. F of x is an exponential function with a linear exponent. Therefore, f of x is continuous on the entire real number line. And what that means is that there will be no holes, jumps, or gaps in the graph of f of x because you can substitute every real number in for x and get a real number back. All right, so now that we've answered that question, we can go ahead and apply the fundamental theorem of calculus. So if lowercase f of x is equal to e to the 2x minus 3, then an antiderivative of this function is the following. So the definite integral of 0 to 2 of f of x is equal to an antiderivative evaluated from 2 to 0, and we're going to subtract the results. So here we go. The antiderivative evaluated at 2 is equal to the following. This is e to the 4th power divided by 2 minus 6. F of 0 is equal to this. E to the 0 is 1, so please make sure that you do not write 0 here. E to the 0 is 1, so this is going to be 1/2. So the difference looks like this. So this is equal to e to the 4th divided by 2 minus 13/2. And so the definite integral is equal to e to the 4th divided by 2 minus 13/2. Just going to rewrite that a little bit, make it look a little neater. And then you can use Decimus to give an approximate decimal value, so that's 20.799. All right, so what does this number represent? All right, so back over here to the graph. Here's the graph of f of x, and the area that's positive is in green, and the area that's negative is in red. And if we take the area in green and add it to the area in red, you're going to get, make this a little bit bigger, the value of e to the 4th divided by 2 minus 13/2, which is approximately 20.799. So that's what the value of the definite integral represents, and we are done.